Yeah, so thanks everybody for coming, and we're delighted to have Feng Xu with us today. And he's going to tell us about some things related to CFTs and von Neumann algebras and things like that. And he'll be giving a series of 2 lectures. So take it away, Feng.
Okay, all right. Good morning, everyone. I'd like to thank Zhenghai for giving me the opportunity to talk. So yeah, like I said, please do interrupt me anytime you want. This is going to be a really elementary talk. So I didn't see the participants here. So let's see. Yeah, I think I would apologize to those of you who probably know the stuff well, but I think most of you probably haven't heard my talk before. So anyway, so yeah, it's going to be really, really elementary. I will emphasize on the basic concepts and give examples, I hope. Anyway, so I'm going to share my screen now. Now, the problem with my iPad is that when I share my screen, I wouldn't be able to see you guys. I should probably log in with another device, but I haven't done that yet. But let's see how it goes. So please do interrupt me. So I'm going to start. Okay. Yeah, so let's see. Okay. Okay, so yeah, so let's start with, so we're going to start with the notion of von Neumann algebras. Okay, so can you guys see this?
Yes.
Okay, yeah. So I'll be like, I'd be like writing on the screen and wouldn't be able to see anybody. So yeah, just give me some feedback if you can. Okay. So I think I will start with Hilbert space. So so usually we will let H be a Hilbert space. And let me be very concrete. So what's a Hilbert space? So I assume most of you know that, but if you want a concrete example, here's the example. So here's the example. So if you take, let's take a group. The 2 groups I would like to consider in this lecture. So the first group is going to be free group on 2 generators. Okay, so this is free group on 2 generators. It's probably the easiest one to describe. So in other words, this is non-abelian, okay, non-abelian. So which means it's just, it's just a group generated by 2 letters A and B, and there are no relations between A and B. So it's a large group, it's a discrete group, okay? So that's one example. So what would be my Hilbert space? So my Hilbert space would be just the little L2 of F2 of F2. So what does this mean? This means that I'm taking all the functions from this free group in 2 generators to complex numbers so that it has the following property. If I, this is such a large space, but if I take the L2 space, so if I take a G in F2, I require that if I sum over, the absolute value of Fg squared, it has to be less than infinity. Okay, so this is the free group on 2 generators, and I'm considering all the functions on F2 with some this is what's called L2 condition. So this is what the little L2 stands for. Okay, and this is a Hilbert space. Okay,
yeah,
this Hilbert space.
Questions. Sorry.
Yeah.
So here I think a free group means all the group elements are words formed by letter A and B. Is that
correct?
Right?
Yes.
Okay.
Yes. Yes.
Why
so
you do this free group? That's complicated. Why don't you have 1 word? So that's Z.
That's also very good. Yes. Yes. That also would work in describing a Hilbert space. But I will describe an algebra later, and in that case, if you take just 1 word group, the corresponding algebra would be not terribly interesting. So yeah, you're absolutely right. So if I take if you take Z, so if you have just one word, that will generate the set of integers. Little L2 of Z is also a hyperspace.
Okay.
Yeah. So no problem with that.
But the structure is not so good.
Yes. As a hyperspace, you know, all the separable, all the infinite dimensional separable hyperspaces are isomorphic. So all of them as a hyperspace, it works perfectly fine. You know, the reason I introduced the player, this non-abelian free group on two generators, it's because of the algebra, you know, because I want to talk about phenomenon algebra, interested in phenomenon algebras in a minute. So that would be useful. Yeah.
Another question is that why it had to be infinite dimensional hyperspace? Why not finite? For example, you can choose your group to be S3.
Yes, absolutely. Yes, you're absolutely right. Yes. So yeah. So I'm not saying that every hyperspace is like this, right? This is example, right? Of course, if you take a finite group. So yeah, absolutely. So if you take a finite group G, let's see, the order of G is less infinity, then L infinity of G is just a G-dimensional, finite hyperspace. Yes, absolutely.
I can say one thing. The reason he chose this one is because this is the one will be most interesting. The one you mentioned, he understood so well, he didn't want to talk about it.
No.
I see.
No. No. It's I can of course yes. I take, there's so many examples. You know, for most of you know that if you talk about the finite dimensional hyperspace, you basically you go into linear algebra, right?
Yes.
Yeah, that's what we do, right? I mean, that's of course a very important part of undergraduate education. But infinite hyperspace is certainly more interesting. You know, for mathematicians, they're more mysterious. Okay, but I'm not saying that finite dimensional lines are not mysterious. I mean, there are plenty of open questions, right, in the finite dimensional world. But they're all interesting, I think. But I will, for this talk, I'll probably emphasize more on infinite dimensional hyperspace.
Okay.
Yeah.
But this L2 means all the vectors are normalizable. Oh, I see. This F.
Yeah.
Okay,
So in the finite dimensional case, of course, this is not terribly interesting because if G is a finite group, then this is just a finite number of elements, right? So this condition is empty. Okay. But in the infinite group case, this is a non-empty condition because so this function assigned to every element in the group a complex number. So there, in general, you got infinite number of non-zero elements, and you require that this sequence is not arbitrary; it's sort of bounded, right? If you take this absolute value square, when you add it up, it's going to be a finite number. So this is a constraint there.
Yeah, I understand.
Okay.
So
yeah, also, you might wonder why you take L2, because if you take L2, then you have the inner product. So this, so if you take any F and G in this L2 F2, then you have the inner product. The inner product we all like. You know, this is what distinguish hyperspace from the rest of the complete norm vector spaces. So if you take F, I guess I forgot which notion, which convention this is. This is probably mathematician's convention. So we take F bar times G and just sum over. Oh, I use the same G, sorry.
That's okay.
Just in this case, yeah. So it's sum over all these elements. So this is inner product.
Okay, yeah. So now I understand. But there's a physics motivated question. Is that in physics we usually have a finite dimensional system.
Yes.
But however, we want to take a limit where dimension go to infinity via the finite dimensional hyperspace. So from this point of view, whether choice of L2 be more reasonable in the sense that L2 maybe naturally is a limit of a finite dimensional hyperspace.
Yes, absolutely. Yes, from hyperspace point of view, yes, that's true. So for instance, what you can do is F2 is a discrete group. So it's a countable discrete group. So you can start with, you know, you know, those elements, right? You take a larger and larger finite set, and then that will approximate the Hilbert space L2 of F2. Yes.
Okay. Yeah. Thank you.
Yeah.
Maybe I will make two comments here. So one is I think it's a question for Xiao-Gang and Wu Laoshi. So, you know, he take F2. You guys as physicists, you really should think about a particle move on a figure 8. Because F2 is the fundamental group of a figure 8.
Figure 8, yes.
And Z is the fundamental group of a circle. So you really should think about the particle move on the figure 8. But the comment I really want to make is that, you know, it's a long, you know, kind of standing philosophy that you think, you know, infinite dimensional Hilbert space is nothing but approximation by finite dimensional Hilbert space. But I think a recent theorem says that's not a good idea if you want to be really subtle. So there's this new theorem, MIP equals RE star, that says basically there are infinite properties you cannot really capture well by using approximation. So there are subtle properties you have to go to infinite dimensional Hilbert space.
Yeah, but Zhenghai, that's a good comment. But I was also wondering if that's a theorem yet.
You think you want the theorem is correct or not?
Yeah, because there's a new updated version.
Well, okay, that's I don't know. I'm assuming the theorem holds.
Yeah. Okay. Yes.
But my comment here is that anything which is beyond this finite dimensional approximation is so-called unphysical. So we don't worry about that.
That could be true. That could be true. Which is there are no algorithm to do this approximation. But I think it's a very subtle question.
Yeah. Thank you.
Yeah, it is. Yes. But on the other hand, for mathematicians, we love the infinite dimensional world. There's so many wonderful things happening there. So I think nature might take advantage of that.
Okay.
This is a very important point, which is, our, physical properties can always be approximated by finite dimensional systems. I don't have an opinion on this. I hope not, but who knows?
Okay. Yeah, that's a good point.
Okay. All right. So let's continue. So as you can see, I was saying that this L2 condition is really important because otherwise, because you sum over infinite number of elements of the complex numbers might not make sense in general, right? But this makes sense because the Cauchy-Schwarz, right? So maybe the X value of this is bounded by little L2. So maybe I'll write norm of F times the norm of G. So where the norm of F is just sum over the group elements squared. Take the square root. So this is so-called Cauchy-Schwarz inequality. Okay. So this is my Hilbert space. Okay, and then I have said that all the separable infinite dimensional Hilbert space are isomorphic. Okay, but if your Hilbert space is finite dimensional, then there's only one quantity that distinguishes Hilbert space from the other. That is the dimension. So two Hilbert spaces isomorphic if and only if the dimension are the same. Okay, so that's the notion of Hilbert space. And of course, this is our playground, and my goal is really to introduce what are the algebras on the Hilbert space, right? So there's one.
I have a question before you go on.
Yeah.
This I heard this so many times, but I wonder the other. So you mentioned this, of course, finite dimensional. The only thing important is the dimension.
Yes.
If you put a condition separable, infinite also have only one Hilbert space. But suppose you drop separable. Is there a way to classify them by something?
It's determined by the cardinality of the basis. So
it's always determined by the cardinality of the basis.
Yeah. So if your basis, let's say if one has cardinality, let's say A1, the other one A2, so then they're isomorphic if and only if that's A1 is the same as A2.
So separable is not terribly important. It's just if you fix the cardinality of the basis, that determines the Hilbert space.
Yes. Okay. But usually we like separable because separable means that it has a countable basis. So separable, so countable. So H is separable. Yeah, sorry, I used the language I didn't, terminology didn't explain. So H is separable if H has a, let's say, countable basis. Okay, so this means that, you know, so basis means that elements can be expressed as a linear combination here. So let's not go much into that. So yeah, so most of the time we were dealing with separable Hilbert space. They're exceptional cases, but from my experience, all of them more or less related to logic. Okay, so when you go to you know the continuum and all that, you know, that kind of thing. So that's really not the focus of these lectures. Okay, are there any more questions on Hilbert space? Okay, so yeah, so let's go to the algebra. So yeah, so Zhenghan, can you remind me, this is a 1 hour lecture, right?
You are scheduled for 2 hours if you want.
Oh, 2 hours. I probably won't be able to do that much.
No.
Okay.
You can. It's we scheduled for an hour, but you know normally it go to an hour and a half because there are so many questions.
Yes, I can see right now because I have barely introduced any concept yet except Hilbert space.
Well, you will see.
Okay. All right. Okay. So let's start with what I call B of H. Okay. So B of H is the space of all the operators from the Hilbert space to itself. Okay. And this is T is linear and bounded. Okay, so it's the space of all bounded linear operators on the Hilbert space. Okay, so maybe if you have never seen this before, maybe one example would refresh your memory from linear algebra. So one example is if you take the Hilbert space to be finite dimensional, let's just take it to be Cn, n is finite, C is complex numbers. So this is the complex in plane with the standard inner product. Then this B of H is the space of all linear operators from Cn to itself. So this is what's called the matrix algebra. Matrices of yeah, so n by n matrices. Let's just write n by n matrices. So n by n matrices. Set of n by n matrices. Okay, so this is a you know, since what we mostly interested in the infinite dimensional case, so this is a really infinite dimensional space, and it has very interesting structures. So maybe I will say those structures on the set of n by n matrices. So B of H is an algebra. Okay, right? If you have matrices, you can add them. You can also multiply them, right? So that's additional multiplication, okay? So here, if you have linear operator, you can compose them, right? T from H to H, T1 from H to H, and T2 from H to H, you can compose them. You can also add them, that's still linear. The bounded, this notion of, you know, boundedness is introduced specifically dealing with infinite dimensional situation, right? Because if you have finite dimensional case, then all the matrices, I mean, all the linear operators bounded. So B of H is an algebra, and also with a star structure. Okay, so what is the star structure? So in the case of matrices, so if T is an n by n matrix, but what is the T star? So T star is just T. You take these transports and they take complex conjugate. Okay, so that's the star operation. So in general, you might wonder, how do you define the star in a general Hilbert space? Well, you use the inner product. So let me move this up. So so in general. So let's say I have psi eta in the Hilbert space, and T is a bounded operator on on the Hilbert space. So how do I define star? So you use the inner product. So T psi eta is defined to be psi T star eta. Okay, so this is how the star is defined. Okay, and you can see in the case of Cn with the standard inner product, that gives you exactly the complex conjugate and transports. So this is how, in general, this T star is defined. So BH is an algebra with a star structure and also contains identity element, right? BH contains identity element. So identity element is what you think it is, right? Identity element belongs to B of H. So identity element is simply a map which maps every element of the Hilbert space H to itself. Okay, so algebra star identity element. Okay, so that's our first example. Okay, and BH in this case is actually for Neumann algebra. Okay, okay, but I want to really define the general for Neumann algebra. So how do I do that? Well, I need to introduce a bit of topology here. Okay. The topology I will define, maybe I will do it using the weak topology. Perhaps that's more familiar to physicists. So the topology I want to define is the following. So we say that, so this is the weak operator topology.
Excuse me, maybe before you define topology, I have one question.
Yeah.
About the bounded. There's another way to define bounded, at least, I mean, as this summation of absolute value square of a matrix element are finite. Okay.
Yeah.
And whether this definition would exclude identity operator. So that's
yes.
Maybe that's a reason why we don't use that.
Yeah, that's a different topology. Yes. I'm trying to think what kind of topology you're referring to. That's yeah, that's a very different topology from the topology I'm talking about.
It's like compactly supported or something like that.
Yeah, it's compact supported, and I think it's even more than that. If you take all the matrix elements and add them up. Yeah.
I think Xiao-Gang, you are thinking something different. So the bounded here really means, the largest eigenvalue is,
Yeah.
Yeah, it's finite. Yes,
but the bounded, another way to define bounded is the operator itself is bounded.
Well, that's the operator. Well, that depends on how you define the operator norm.
Yeah, yeah.
That's a bad norm, I think. Yes.
Okay.
Yeah. We yes. So that's absolutely right. I'm sure there are people who study that. This is such an old subject. I'm sure those corners have been touched, but yes, there are lots of topologies there. So yeah, I would just define one topology for the purpose of introducing for Neumann algebras. Yeah.
Okay. Yeah, that's helpful. So this topology are related to how you define operator bound or something like that.
Exactly. Yes. Okay. Yes. Absolutely. Yes. Yes, and this, of course, this is what why the infinite dimensional world is interesting, because all these topologies are different. Okay, if you restrict the finite dimensional Hilbert space, all these topologies would coincide.
By the way, Xiao-Gang, to make you happier, I'm a topologist. I'm embarrassed to be confused by so many different topologies.
Yeah, but don't worry. I'm still confused by these topologies. So last time I count, there are 7 different topologies, even in the phenomenon world. But usually, it's 1 or 2 that stands out. Yeah, the one I'm going to talk about is the one I hope you might like. I mean, especially the physicists in the audience. Yeah. Okay. So weak operator topology. So what is this topology? So suppose that topology, I mean, there are various ways of introducing topology, but maybe I will introducing, so topology is basically telling you how things are close to each other, right? So we say that Tn, this is a sequence in B of H. We say that Tn goes to T in weak operator topology if the following is true. If for any psi eta in the Hilbert space, you take sort of expectation value of this operator, this is going to be a complex number now, right? So this is a sequence of complex number. This sequence complex number converges to the corresponding expectation value of this operator T with this two-factor psi and eta, okay? So this is a weak operator topology, okay? So I thought physicists might like this because, usually in quantum mechanics, Tn would be your observables, right? Like position or momentum or energy. And we say that, this operator, this observable approximate, is close to another observable. If you do experiment, under this psi eta, the result converges to the experiment of under this condition, this is like the preparation of a state, and then your result would converge in this sense, right? So hopefully this is the this is the topology that seems to be quite natural. Okay.
So the question is that here you do not require uniform convergence, right?
No uniform convergence. So this depends on, yes, absolutely. This depends on psi and eta. Okay, so if you prepare the state, let's just put eta to be the same as psi. You can do that too. So it depends on the state. Okay, so the rate of convergence, depends on the state. Yeah. So this is rather weak. So this is a weak operator topology. Yes.
And I agree. This is a good topology for physics, because this is really says you don't care about the states. They are kind of just in your brain, but you care about the correlators.
Yeah, that's right. So anytime you prepare a state, these observables will converge. This sequence of observable will converge to T. Yes.
So there's another motivation, as you mentioned, that all these different topology became degenerate for finite dimensional Hilbert space. Okay.
Yes.
So if we using philosophy that we're interested in the limit of finite dimensional Hilbert space, it looks like if using this motivation, one would try to find a topology which somehow have best properties for infinite dimensional Hilbert space, because eventually they will be all this will be degenerate. So that will be another motivation to looking for what kind of topology we want to assign for infinite dimensional Hilbert space. And so in this context, so whether this weak operator topology is a good, or whether there's some even better behaved operator topology, with a stronger constraint, a better property or something.
Actually, Xiao-Gang, this is a good discussion actually. So first, I want to ask your opinion. You don't like this weak operator topology? Because this is, to me, this is kind of almost the only one.
Okay. It's not I don't like it. I like it. But my question is following, because you mentioned there's several different topology.
Yeah.
Then I just want to have some kind of expression or some feeling. Which topology have a better property, stronger property, which topology have a more nasty property,
maybe we can ask Feng Xu to explain another topology, the operator topology will give you the C-style algebra. I think that's the two.
Yes. So yes, that's another subject. But since we're talking about topology, so obviously there's another topology. So let's take the norm topology. That's obviously stronger. So we say Tn goes to T in norm. Sometimes people just write the norm symbol there. So this is pretty straightforward. If you take Tn minus T, that's a linear operator. You find its norm, this goes to 0, right?
I see.
So this is absolutely much stronger than that. And so weak operator topology is certainly weaker. Okay, if you have Tn converges to T in norm, then of course Tn converges to T in weak topology. But on the other hand, it's not the same. So this is a good exercise. I usually give them to my functional analysis students. Show that.
I need to do that.
Yeah. So show that for B of H, so norm topology is the same as weak operator topology. On B of H, of course, this is the only player we have said so far, if and only if the dimension of a Hilbert space is finite. Okay, so this is what I was saying earlier, that it's really in the infinite dimensional world we see all of these differences. Okay, otherwise, yeah. So in the finite dimensional world, all these topologies coincide.
Yeah.
I think in the finite dimensional world, all the reasonable topology you can think of coincide.
But my question is following: whether, for example, these two topology, weak operator topology and norm topology, which have a better property, mathematically it looks nicer.
Oh, they're all good. They're all good. So yeah, so norm topology, as Zhenghai mentioned, would lead to what's called the C-star algebras. Okay, that's of course a very important chapter in the theory of operator algebra. But the weak operator topology is more important in what's called von Neumann algebra, which is what I want to emphasize.
I see.
Yeah.
Yeah. So I can make a comment here. So if you want to think about the difference between topology, these two topology, actually there's a philosophical point. So if you study, algebra using C-star topology, you are basically doing some kind of a non-commutative topology. But if you study using the von Neumann, the weak topology, you are studying non-commutative probability theory. So they are very different.
Magic theory, yes.
I see.
Yes. So yes.
Like, I don't know whether my feelings are right. That looks like a C-star algebra maybe is too close to the finite dimensional Hilbert space. So maybe von Neumann algebra capture some actual property of an infinite dimensional Hilbert space.
I think it's true.
That's probably not true. Most of the interesting. So yeah, so most of the C-star algebras, people interested in all infinite dimensional. So yeah, maybe I will give you example right on. So but Zhenghai made a really good point. So von Neumann algebra is like more like L infinity. So this is more like non-commutative measure theory. And C-star algebra is more like a non-commutative topology. Okay. Yeah. So in measure theory, points do not matter, right? So if you remove a point, let's say on the blackboard with the usual big measure, it doesn't matter because it's measure 0. But if you're on a circle with a topology, if you move a point from the circle, it's no longer a circle topologically, right?
I see.
So they're very, very different.
Okay, thank you. Yeah, that helps.
Yeah, sure. So let's see. So norm topology, of course, that's a different chapter. So I should say that this is also very important. I mean, for people doing K theory, this is very, very important. And this, I think, is also related to topological phases, but I haven't checked that the literature in that direction recently. But anyway, so so let's see where I am. So I introduced weak operator topology. Okay, so finally I'm ready to define this. The von Neumann algebra I was saying before. So a von Neumann algebra. So let's say M belongs to B of H is called a von Neumann algebra. If the following condition is true. So first, M. So if identity is in M, M is in star subalgebra. Okay, and M is weakly closed. Okay, so let's see what is this condition. So we require identity element in M. That's not terribly important, but it's convenient. And M is a star subalgebra. So M is a subset of B of H. BH is a star algebra, right? It's an algebra with a star structure. So what I mean by star subalgebra, I just means that if T is in M, then T star is also in M. So in other words, M is star closed. And then the last condition. So these are algebraic condition, and the last condition is a topological condition. We asked the M to be weakly closed. So this means that if you got the Tn in M, and Tn converges to T in weak operator topology, then this limit, the weak limit, also in M. Okay. So this seems to be a lot for those of you who have never seen this before.
A question here. A question.
Yeah.
So, do we require the Hilbert space to be separable, finite dimensional, or there are no constraint on H at all?
Separable is just a convenience. Yes.
So we don't need any condition.
No, just H is a Hilbert space, and this is what I'm giving you is the definition of von Neumann algebra. No other things attached.
But then my question is, for every von Neumann algebra you can choose H to be either finite dimensional or separable, or that's not true?
No, that's not true. Okay. Yeah, people are interested. I mean, there's chapter. Yes, that reminds me. I should give you guys a reference at the very beginning. I forgot to do that. Yeah. So yes. So for my so this is this is what I will base down. So the references I should have written this very beginning. So for the 2 lectures I'm preparing, it looks like I probably only cover some of this. So the reference on the CFT and operator algebra approach is so there's first one. So maybe I will say von Neumann algebra first. So one of the very good lecture notes, these are lecture notes by Von Jones. So it's in his Vanderbilt website. Okay, you can find so the title is simply von Neumann algebras. I find these lecture notes exceptionally well written. Okay, and the second one. But then if you want like an encyclopedia version of those things, including many more things, this is the Takesaki by Takesaki. Okay, so I think it's called Encyclopedia of Mathematics, and the title is also von Neumann algebra. So there's volume 1, 2, 3 here. Okay, and to tell you the truth, even up to this day, I'm still occasionally, looking through some of those. So the one thing I like, especially about Takesaki, is that at the end of each long chapter, there is a very short section about historical comments and so forth, and it's very enjoyable. So. If you have nothing better to do, just read those notes and think, it will be interesting. And third is more towards the von Neumann algebra stuff, so the operator algebra approach to quantum field theory stuff. So there is a paper by Long joined with by Longo and Katz. So I wrote this paper with Longo and Katz. I think it's around 2005. I believe it's in CMP. And the reason I'm referring to this article is because we actually spent quite some time. Katz is it's a specialist in representation theory, but so he asked so many questions. So the motivation that this joint project initially was motivated by his question, and we solved it by using von Neumann algebra techniques. But he had so many questions, and we decided, so just to satisfy him, we decided to write what I thought a thorough introduction to the operator algebraic approach. To conformal field theory or quantum field theory in general. So we write a long introductory part to that with, I thought, all the concepts. And so Victor Katz seems to be satisfied with that. So I thought I might share that with you. But anyway, so this is the reference. Yes. So what I was saying is that, what I'm saying. Yeah. Okay. Yeah, I forgot what I was saying before.
Well, you were interrupted by my question that the Hilbert space can be any dimension.
Oh, yeah. So in Takesaki, there is actually, I think, there's one, if I remember correctly, there is actually one section where he discussed the non-separable case. Okay, But then after that, there's a sort of pessimistic note which says that these days the non-separable Hilbert space and non-separable for non algebras. By that I mean for non-algebras with non-separable predual. Then he commented that this seems to be out of fashion. That's his words. But anyway, yeah. So this is complete general. Yeah. Okay. So as I said, this seems to be a lot, right? The star algebra has to be weakly closed. You know, you impose algebraic conditions and topological conditions. So I guess I will introduce the first theorem in the theory for Neumann algebras, not surprisingly due to von Neumann. That M belongs to B of H is a von Neumann algebra if and only if M is equal to its double commutant. So yes. So I will have this notation here. Let me tell you what this is. So if A in B of H is any set, A prime is defined to be another set. So it's defined to be the commutant. So this is OT in the B of H, such that TA equal to AT for all A in this set. Okay, so that's the definition of commutant. Okay, and let's look at the von Neumann's theorem.
So Feng, do you
Yes.
need to require M to have the unit? I just wonder if you can derive the unit from double commutant.
Yes. This is how I define, right? Identity. So commutant always contains unit, right?
Oh, good. Okay, thanks.
Yeah. So yes. So let's actually look at the theorem. I guess it's almost everybody's favorite theorem, one of the favorite theorems in von Neumann algebras. So let's look at this result. Okay. So the double commutant, right? So this means commutant and commutant. So it means you commutant first, and then you take a commutant again, right? So that's the notion of double commutant. Okay. Now let's look at this theorem. Okay, and just compare the definition. So because of this theorem, you can take either of one of this as your definition for Neumann algebra, right? You can define for Neumann algebra to be what I define here, which is a mouthful, the algebraic structure, and also close under topology, or you can define this just simply using algebra, right? You take M, you take its commutant. Commutant only use the notion of algebra, right? It's elements commuting with the given set, and then commutant again. Okay, so the right hand side is purely somehow algebraic, but I'm actually cheating a little bit because everything happens in B of H, right? That's already with a topology and so forth. Okay, it has to be space of bounded operators, right? But at least formally, the right hand side seems to be purely algebraic, where the left hand side depends both on algebraic structure and being weakly closed. That's a topological condition, right? So this is a beautiful theorem, and it shows that the theory for Neumann algebra is closely tied with both algebraic and analytic structures. Okay. Anyway, so yeah. So now you can produce a lot of examples by using.
So Feng, I know you don't have time to prove it, but can you give like a few sentences, like what's the point? Because this is so deep. I'm always amazed by this theorem, but I have no idea what's the point. So can you say a little bit like why the double commutant can capture topology, from this algebra?
Yes, absolutely. So maybe one comment. The actual proof is actually sometimes actually not hard at all. So,
okay, but I think I'm looking for a philosophical point, like how come this can be true?
Yes. So maybe one thing I can comment is that the commutant is always star closed. Okay, so maybe just one comment is here, is that even though you define a commutant like this, so A prime is always is weakly closed. Sorry, is weakly closed.
Maybe that's the point then.
Yes, right.
Oh, I see. Okay, I got it now. Okay.
Yeah, because if you use this condition, yeah. So maybe I'll say to the rest of you. So if you have Tn goes to T, and if each Tn commutes with A, it follows easily that T also commutes with A, because checking commutativity just amounts to checking on the vectors, right?
Okay.
Yeah. So yes. So commutant is always weakly closed. So then you realize that since now you also see why we require this to be weakly closed for this theorem to even have a chance, right?
Yeah. Okay.
Because
so I think
the right hand side is weakly closed.
The commutant actually is more than algebra. It's actually closed. So that's
yes, that's right. Yes, this is what I'm saying earlier, because you know, everything happens in B of H. So B of H already has an topological structure. Yes, it has to be the space of bounded operators. It doesn't work if your operator is unbounded.
So if for the C star algebra, this will not be true. Is that right?
No. Yes. That's yeah. So C star algebra has So C star algebra will be closed under the norm, and this wouldn't be true because the commutant introduced a lot of more elements.
Okay. Yeah.
Yes. Yeah. Okay. Yeah. So this is the first theorem for Neumann algebra. So let me see what's my next thing according to my notes here. So far I give you just one example. So let's look at examples. So obviously B of H is a von Neumann algebra. Okay, that's pretty clear from the definition, because because everything happens in B of H, so all these conditions trivially hold, right? Weakly closed and so forth. So B of H is a von Neumann algebra, and this is what's called the type 1. Okay, so this is like a matrix algebra when H is finite dimensional, and when H is infinite dimensional, it's infinite algebra, but we think of this as something which is rather classical. Okay, so B of H is a von Neumann algebra. To move further, let's give another example of von Neumann algebra, and that's where the reason I introduced this F2 here. Okay, non-abelian free group on 2 generators. So that's my next example. So remember the little Hilbert space, the Hilbert space L2 F2. Okay, these are L2 sequences on the free group on 2 generators. And notice that if F2 X on this Hilbert space by translation, by maybe let's write left translation. Okay, let me define this. So let's say I have a G in F2, well, maybe G in F2, F in L2 of F2, right? So I want to define an action of G on F. So how do I? So I'm supposed to get an element also in L2, right? So what's this action? So G acting on F is supposed to be a sequence on F2. So I just have to tell you what the sequence is, right? In other words, I need to tell you what this sequence is on any element in F2. Okay, so the definition is very simple. It's F G inverse acting on H. Okay. So this is left translation. Don't worry about this G inverse. Just make sure it's a convention. It's a way so that make this into an action. Okay. So what does it do? Well, it's just So the first observation is that the norm of G acting on F is the same as the norm of F, right? Because it just shuffles the sequence, right? By acting on the left by G inverse. So as a sequence, if you take the L2 sum, you still sum over all the group elements. So in other words, the norm is the same. So this action preserves the norm, okay? And also this definition here makes sure that this is really an action. In other words, G1 act on G2, act on F is the same as a G1, G2 as a group element acting on F, okay? So this is in group theory, this is very important representation. This is called a left regular representation. Okay. All right. So yeah. So so why this representation is interesting? Well, you know, even in finite dimensional cases, this is an interesting representation, right? Starting with group elements, starting with a group, you can just produce a group action by acting on the left, right? So this is an infinite dimensional version of that, okay? And this representation, this is a unitary representation because it preserves the norm, okay? So now I'm going to produce a phenomenon algebra like out of this. So what we do is we take a linear, so I guess I will introduce a piece of notation. So so G acting on F, by abusing notation, I would just, G corresponds, or is represented by a pi of G, and a unitary operator from little L2 of F2 to little L2 of F2, okay? So this is a unitary operator. Maybe I will write, instead of pi G, I will write U of G here. Okay, U stands for unitary, okay? All right, so, and you can see that if I take a linear combination, so UG is an operator, I'm taking a linear combination, finite. So let's take G, so CG not equal to 0 for finite many G, okay? So these elements are bounded operators on the Hilbert space L2, F2, right? So take this linear combination, okay? And then we can take this double commutant, or according to Von theorem, the same as weak limit. So if I take the following, G, CG, UG, so all these CGs, and I take the weak closure, let's use this notation, that's the same as taking CG, UG, and take its double commutant. This is a phenomenon algebra. Okay. Yeah. So you know you can take, you know, so yeah. So maybe I should say that the CG, this finite linear combination is obviously a star algebra, right? Because you can add them when you multiply them. It's still elements of this form, and it's a star algebra because UG star is UG inverse, right? So this is a star algebra. So what you're doing here is simply taking its weak closure because you want to get phenomenon algebra out of this. Okay, that's the same as take that double commutant. Anyway, so you should think of this phenomenon algebra as, you know, a dense subset of this phenomenon algebra. It's just finite linear combination of these unitary operators coming from the left regular representation. Okay. So yeah, so that's another phenomenon algebra, and what's interesting about this phenomenon algebra is that there's a distinguished state on this phenomenon algebra. I will give a notation for this. This is the standard notation. We write LF2. So this is the what's called the group phenomenon algebra. So this is the example of group phenomenon algebra. Okay. Now, this group phenomenon algebra has a very distinguished state. There is a distinguished state, which I denote by trace on this phenomenon algebra. Okay, so it's a state, which means the following. So trace, I will write elements X here. So it's linear. For all xy in LF2. Maybe it's normalized. Trace of identity element is 1. And of course, the most important property is the tracial property. So the trace of xy is the same as the trace of yx. Okay. Okay, so maybe I should define the trace before I write down the property. So the trace of an element x is just x delta E, delta E. Okay, so delta E is the delta function of the identity element. Okay. Yeah, so maybe I will write here. So what is delta E? Delta E is an element in L2 in this Hilbert space, right? So it just assigns 1 to identity element and 0 elsewhere, right? This is a sequence, but this sequence only assigns 1 to identity element and 0 elsewhere. So it's a fun exercise to actually check that, verify the tracial property. So trace of X, so if you define this data like this, it's a fun exercise to check. Just check on the elements here, you find that the trace of X delta E is the same as delta E. Sorry, trace of XY is the same as trace of YX. Okay, so this is a distinguished property. Okay, all right. So maybe why this so? Let's see. Let me move down a little bit.
Excuse me.
Okay,
could
so
you explain this delta E again? Let me be a little confused. So this
yes.
L square F2 is a Hilbert space.
Yes. So
yes.
So L2 of Fn is a Hilbert space, right? This consists of all those functions F from F2.
Oh yeah. Okay.
C. Yes. Yes. So delta E is a function, so that its value at point G is delta function, right? Delta G.
Oh, yeah. Okay. Now I see.
Yeah. Just assign 1 to identity element.
Yeah. Okay. Now I see.
This is really easy exercise. So to check, I mean, the tracial property. I have given you everything, the definition, and I think it's a fun exercise. You just take good elements of this form and then you just check. It's pretty simple. It's pretty straightforward to check the tracial property. Okay, but since I talk about the trace, maybe some of you might be familiar with the trace we learned from linear algebra. So just recall that if you have matrices, so let's say matrix. Well, I will write a matrix of size n like this. Okay, there is a trace, right, from the matrix of size n to C, and the trace of let's say a matrix Aij is just the sum of a diagonal, right? That's what we're familiar with. But notice my trace is normalized. So trace of identity element is supposed to be equal to 1. So we divide this by n, right? That's the usual trace we're familiar with in linear algebra. One of the important property, why you sum over the diagonal is because the trace of AB. So it satisfies this tracial property, right? You can do the cyclic permutation, doesn't change. Okay, so this is similar to that. Okay, so this second example gives for Neumann algebra together with a distinguished state, a tracial state, okay, which verify this property. Okay, so here's a fun exercise. This is probably slightly harder. So you see, I have given you 2 examples of von Neumann algebra, right? Start with, we have B of H, and then I claim there's another von Neumann algebra, right? But there's no guarantee why these 2 von Neumann algebras are different. Okay, so here's a fun thing, So let's sort of show LF2 is not the same as B of H. Okay. Okay. So so how do I show that? Well, I know LF2 has a trace, right? So if they're isomorphic, then this trace would be defined on B of H. Okay?
You mean B
but
of
also,
H is the L2 F2, right?
No, I use the notation here. So this is a von Neumann algebra, and I denote it by this.
Okay, yeah.
So this is I mean, this is not the notation I invented myself. It's a sort of standard notation. Yeah. So L stands for left regular. Okay.
Yeah.
And so this is what's called a group von Neumann algebra. You see, there's no reason to just choose F2. You can choose any discrete group. So if you replace F2 by any discrete group, you also get a von Neumann algebra. Yeah. So this is what's called a group von Neumann algebra. Yeah. It's a von Neumann algebra coming from groups.
But what I mean, the H is L2 F2. The B of H.
Yes.
The H
yes.
Is
yes.
Yeah,
That's
okay.
Right. Yes.
Yeah.
The Hilbert space is L2 of F2.
Okay. Yeah. Thank you.
That's the Hilbert space that I started with. Okay. So let's see why this is not isomorphic. Well, this LF2 has a trace. So if they're isomorphic, then there's a trace. So there's a trace on B of H. Okay, if LF2 is isomorphic to B of H, then there's a trace on B of H, right? But remember, you see, F2 is so huge, this is certainly infinite dimensional, right? So if the isomorphic, this Hilbert space is also infinite dimensional, so H is infinite dimensional. Actually, otherwise, this is a matrix algebra, it's finite dimensional. But you can see this F2 is huge because you have all these words in, arbitrary words in 2 elements. So there's a lot of them, okay? So if you claim these 2 phenomenal algebras are isomorphic, then you can have a trace on on B of H where H is infinite dimensional. This is important because we know if your H is finite dimensional, there is a trace. This is a trace we're all familiar with from linear algebra, right? But as soon as you go to infinite dimensional case, then you cannot have a trace on B of H, right? You can see from the formula here already, because you see, in order to get a trace, but n, you can imagine that your infinite dimensional Hilbert space, you let n go to infinity, but then you see this 1 over n is a problem part, right? It's not well defined anymore. There's no such trace. And indeed, this is a good exercise. So there's no such trace on B of H with dimension of H is infinity. Okay, you can sort of see it from here already. In the finite dimensional case, when Hilbert space is finite dimensional, there is a trace. But the way you define the trace, you have this 1 over n here, where n is the dimension of Hilbert space. But in infinite dimensional case, this wouldn't make sense. Okay, and indeed, you can prove this is what I usually give to good students in my linear algebra class. So if you have to show that there's no trace on the B of H. So what I've shown is that there's at least 2 phenomenal algebra, right? For now, LF2 with a trace and then B of H. Okay, and of course you can see that you immediately see that because what I said before, this construction of LF2 is complete general. So in general, G, let's say for convenience, let's take this to be a discrete group. Then LG is a phenomenal algebra with a trace. Okay, so this is complete general. Okay, so right, so that's the 2 example, and in fact,
let me ask you a question here. Sorry, since you have very general statement, if the dimension of a Hilbert space is infinity, then there will be no trace. But yes. LF2 also have infinite dimensional Hilbert space.
Yes.
So, but that have trace. So the difference that LF2 have a group action. So that help you to define a trace. Without group action, then you cannot define trace in general.
Yes. This LF2 is very special. It's related to the group representation, the left regular representation.
Okay.
And that's the that's the key issue. Yes. I forgot to mention maybe why bother with phenomenal algebra in the first place. So Maury and Neumann developed this theory back in the 1930s and 40s. Okay, so Neumann stated 4 motivations for developing phenomenal algebra. Okay, so the first one is the representations of infinite groups. Okay, that's what I remember. The second one is the motivation coming from quantum mechanics. Okay, because in quantum mechanics, you frequently deal with unbounded operators and so forth, and the algebras, they generated are usually infinite dimensional. Okay, and third one is the motivation coming from probability theory. Okay, now I forgot the fourth one. I should remember it, but I got the 3 motivations are good enough to study phenomenal algebra. I think von Neumann himself, he was sort of like a student of Schur, who is who studied representation theory. So he has a strong motivation coming from representation theory. That's why the first few examples, like the example I'm doing here, the group phenomenal algebra, comes from representations of groups. Yeah, another comment people sometimes said during the talk or the beginning of the talk on phenomenal algebra is like, phenomenal algebra is like the applied pure math. You know, it borrows you know, it's a pure math, but it borrows all the things from all branches of mathematics. Anyway, so yeah, so Zhenghai, I'm going to end soon, maybe in 10 more minutes. Would that be okay?
Take your time, but I just want to say, I would rather call pure applied math than apply pure math.
Well, yeah, well, I guess depends on the definition, but anyway, yeah, okay.
Take your time, it doesn't matter, but I think this is great, actually. I think first time I got all the something sticky.
Okay, good. All right, so yeah, so I just so we have this phenomenal algebra. So maybe, and I will give this phenomenal algebra a name as well. So we have just sort of shown that these two are different. So the first one is called type 1, and this one, not surprisingly, would be called type 2, and because it has a trace. So such phenomenal algebra is called type 2-1. Okay. So it's different from type 1, and this one simply refers to the fact it has a trace. Okay, this one has a trace. So any phenomenal algebra with a trace, and of course we're interested in infinite dimensional case, any infinite dimensional phenomenal algebra. So I should such infinite dimensional algebra with a trace. This is called a type 2-1 phenomenal algebra. Okay, so that's very different from B of H. Okay, so before I move on further, so I should, you know, since I talk about what type 1, type 2, there's also type 3. Okay, so type 3 is the complement of type 1 union with type 2. Okay, so this is let's just leave it like that for a minute. I probably today I won't be able to give you examples of type 3. But for physicists, you see type 3 factors every day. You see it at the breakfast, you see it at lunch, and so forth, okay? But maybe you didn't realize it. But anyway, so I will have plenty of type 3 maybe next time. But today, let's just finish with type 2-1, okay? So in general, of course, a phenomenal algebra, so classification problem of phenomenal algebra M. Okay, so let's talk about that. So it's classified into 3 types, but before I do that, let me just mention the building block of phenomenal algebra. So let me define what's called the center of phenomenal algebra. So let's write ZM. So in the notation I've introduced so far, it's those elements in M which commutes with M, all the elements in M. So this is all the elements in M, so that M1 is the same as M1M. This is for all M. So it's this in the center, the central element. Obviously, since we require identity element to be in the phenomenal algebra, of course it contains identity element, right? So C times identity element always belongs to the center. Okay, so let's define what's called a factor. So this is the definition. So M is a factor if the center only consists of scalar multiple or complex multiplication of identity element. Okay, this is a factor. So not surprisingly, every phenomenal algebra can be sort of decomposed in a certain way, and then it will be like sort of direct sum of factors, right? Direct sum with quotation mark. Okay, so factors. So the reason we're going to focus on factors. So these are building blocks of phenomenal algebra in general. Okay. Okay. So a factor is simply a phenomenal algebra whose center is trivial. Okay. If center is not trivial, you can always cut down by the center, and then you can sort of reduce to factor case. Okay. So that's the, that's a story I will not talk about, but I'll focus on factors. So what are the factors so far? So examples. So first of all, B of H is a factor. this is a fun exercise. In the case of finite dimensional case, it just shows that, you know, a matrix, n by n matrix, which commutes with every other n by n matrix, is a scalar multiple of identity matrix, right? But in infinite dimensional case, it's slightly more, but almost the same, okay? So this is a factor. The second one, which is,
excuse me. So here, H is arbitrary Hilbert space, right?
Yes, yes.
Don't have to be L2, F2.
No, no,
Okay.
any edge. Yes,
okay.
Yes. Okay, yeah, so good exercise to check B of H is a factor. In other words, you know, if you think of finite dimensional case, you know, that's an exercise in linear algebra, right? Now, another thing is the LF2 I have just introduced is slightly non-trivial. This is also a factor. Okay, so yeah, it takes a bit more effort to do that, but you can sort of understand why that's the case, right? Because F2 is highly non-commutative, right? It's free group, so there are no relations whatsoever. So, so the center, even though this phenomenon algebra is much bigger because it consists of all this linear combination of, let me move up a little bit, of these elements, it's not too hard to show that, you know, it's still a factor. Okay, this is a complete general fact. So in general, if you take a group G, you take the discrete group, and this is a phenomenon algebra. So let me write down the characterization. It's a factor if and only if G is what's called ICC group. Okay, ICC means that, so ICC means infinite conjugate class. So this means that if you take any element G, which is not identity, G is in G, and you take the conjugate class of G, so just take all the conjugate of this element. This is an infinite set. Okay, so this is what's called infinite conjugate class. You know, this proof, once again, is a rather simple thing. You just compute the center element, you find that it's always, the center element is always supported, is always constant on this conjugate class, but it has to be an element in L2. But so if it's infinite set, then this constant must be all zeros. Okay, so yeah, so this is a general fact, and obviously free group on two generator is ICC group, right? Because there are no relations whatsoever. So these elements is certainly infinite set. Anyway,
but there's looks like this suggests that if H is a finite dimensional, then it's not factor. BH is not factor.
B of H is not a factor?
If H is have a finite dimension.
Yes, yes. But I have written here B of H is a factor. So you're saying this is not correct?
No, I mean, here H have infinite dimension. So if H have a finite dimension, whether B of H is a factor or not.
So it's a
yes. So
only diagonal matrix is in the center.
Yes. So if H is Cn.
Yeah.
Okay. So B of H will be the matrix algebra.
Yeah.
Matrices. So n by n matrices. So it's a fun exercise to show that if you have a matrix, so T is a matrix equal to AT for all n by n matrix A, then it's a fun exercise to show that.
Yeah, I see.
Yes.
So the reason I ask this is following. Because if G is a finite group, IOG will not be a factor.
Yes, that's right.
But H is a finite dimensional Hilbert space. H is still a factor. Okay.
B of H is still a factor. Yes.
Okay.
Yes. Because you see here, B of H is large, right? You have a You're absolutely right. If G is a finite group, LG is not a factor because this condition is not verified.
Yeah,
right?
That's right.
Yes.
So I think
so LG, you see, I guess the confusion here is that this LF2 is not B of H. It's contained in B of L. Yeah. So it's a sub-algebra there. Yes.
Yeah. Okay.
Yeah. So the center will be
another
different.
way to see it. For a finite group, the group algebra decomposes into irreducibles, so they can have different diagonal matrices.
Okay, I think
that's right. Yes. Yes. In fact, you know, the left representation of a finite group is the starting point of group representation theory, right? All the irreducible representation will appear in that decomposition, and with multiplicity, the dimension of the irreducible representation. So that's a classical result, very beautiful result due to Frobenius.
But
anyway,
there's a weird case, which if a group is a trivial group.
No, Xiao-Gang, this is the point. So you should consider.
Okay. You're right.
So Xiao-Gang, this is the point. You should consider n by n matrices for n bigger than 1. That's not commutative group algebra of the trivial group.
Okay. I see.
You're right. Okay.
Thank you.
Okay. So So let's I want to finish with very important thing about 2i factors. So this is So this is the last thing I want to talk about today. So this is what's called continuous geometry. Okay. So let's state a fact. Okay. So maybe so let's take LF2. Just take our example, the only example we have so far. So that's the 2i factor. Remember, it has a trace. Okay. So first of all, let me define what's a projection. Okay. So P in a phenomenon algebra is called a projection if P square equal to P, P star equal to P. So it's self-adjoint and it's idempotent. So P square is equal to P. Okay, so maybe I'll give you example in the matrices. So let's take. P.
I have a question here. I always confuse me. Is a zero map a projection?
Yes.
So it's always considered to be a projection, zero map.
Yes, because 0 star equal to 0, right? 0 square equal to 0. Yes.
I'm always confused.
It's not a terribly interesting projection, but
I know. But the question.
It is a projection. Okay, so let's get a feeling of what projection looks like in n by n matrices. So let's take matrices of size n, or n by n matrices. Okay, so what is a projection if you have a matrix with size n? Okay, so the condition is that P square equal to P star in the n-dimensional case. In the matrix case, star is the complex conjugate and take the transpose, right? Take the conjugate, complex conjugate, and then take the transpose P. So from basic linear algebra, you can see that this P, there's a basis of your, so we think of P as a map from Cn to itself, right? Linear map. You can find a basis of Cn such that this P looks like this. Is a diagonal matrix with ones on the diagonal, ones or 0 on the diagonal, and the rest of entries are 0. Okay, so this is the reason this is called a projection, because you look at what this operator does. So P, let's see, P maps. So P preserves. Let's say this. There are K ones, right? So there's a CK in Cn. This is a k-dimensional subspace of Cn. P preserves CK, right? And on the complement of CK, so Cn is written as CK, direct sum with its complement. This is a orthogonal complement. So P preserves CK, so it acts as identity on CK, and P maps complement to 0, right? So this is what the projection looks like. Let's, I guess we're not in a classroom now. The example I usually use for my students is that if you look at the corner of the wall, and let's say we have a light over there, right? If I hold a chalk, the light is going to project that the chalk out to the ground. Okay, that's what that operator looks like. Okay. Because everything on the ground is going to be preserved, right? Let's imagine we have a light straight ahead, straight above us. Okay, everything on the ground will be preserved, but anything that's orthogonal to the ground will project to the origin, right? Because that's what. Well, let's have that mental picture. So this is what the projection looks like. It's like a projector. It preserves this finite dimensional subspace but maps the complement to 0. Okay, and that's the reason this is called a projection. Okay, any question about projection? Okay, so you see why the eigenvalues have to be either 1 or 0, because p squared is equal to p, right? So the only number that's squared to itself is either 1 or 0. So these are only possible choices. Okay, so this is what a projection is. Okay, and in the case of matrix, so I have written this n by n matrix all the time, so maybe I will write the matrix of size n. Okay, this is little n there. Okay, so one thing is that we know that matrix algebra has a trace, right? Has a trace. Okay, trace, let me remind you again, is just the 1 over n, the diagonal, the sum of the diagonal entries, right? So let's see what this projection, what the trace of this projection is in this case. Well, it's 1 over n, but you sum over the diagonal piece, there's only k of them, right? So it's k over n, right? So k here, of course, is between 0 and n. Okay, so if you look at the matrix algebra, let's write this set, trace of p. P belongs to the, P is a projection. This set, let's look at this set. This set is 0, 1 over n, 2 over n, and 1, all the way up to 1, right? This is the set here. Okay, so I'm writing down this very elementary thing here. I hope it's all clear from linear algebra. Projection, has a space that's preserved, is a k-dimensional subspace, so that's why the projection is always k over n. It's a discrete set. Okay, so now I hope, in contrast with this, the following fact is it's interesting. So if I take trace of p, now this time p belongs to this 2-1 factor. Okay. So this is a fact. This set is the closed interval 0 and 1. Okay, so this is the last result I want to talk about today. Okay. All right, so let's see why this is so interesting and why von Neumann was very excited about this. Okay, so in a sort of finite dimensional world, we see that the trace, the usual trace on a set of matrices, you get a discrete set, right? Now, in the infinite dimensional case, this is an infinite dimensional von Neumann algebra. If you take the trace of a projection, you will fill up the whole closed interval 0, 1. Notice that the trace of p is always between 0 and 1. Okay, because p is less equal to 1. Trace of 1 is defined to be 1, right? So the surprising fact is nothing is missing in this closed interval. Okay, so I guess you can sort of see that, right? But because when you take n to be large enough, it looks like n go to infinity, this discrete set, it's going to be getting closer and closer to 0, 1. But yeah, this is a precise statement. Okay, so if you think of p as describing some kind of subspace, then the dimension of the subspace looks like it's a continuum, right? It's between 0 and 1. Okay, so it's not like it's going to be k-dimensional subspace. Okay, suitably normalized, it can take any value. So for instance, I guess you can find a projection p in the L2 such that the trace of this projection is not a rational number. Let's take pi over 4, for instance. Right? That's a irrational number between 0 and 1. Okay, so that's a very interesting property of 2-1 factor. And von Neumann was very excited about this. He called this continuous geometry, because in the finite dimensional case, projections do correspond to some kind of geometry, right? They correspond to subspace. Okay, so if you think of this as p as some subspace of infinite dimensional Hilbert space, then the sort of the normalized dimension can take irrational values. Okay, so he even have von Neumann even wrote a book on this. The title of the book, I think, is, I forgot the exact title, but it must contain this continuous geometry in the title. Maybe the title of the book is called Continuous Geometry. But anyway, so that's one of the things about 2-1 factor, and von Neumann was very excited about this. And you know, as I mentioned before, one of his motivation of studying von Neumann algebra is you know, motivation coming from quantum mechanics. So he thinks that 2-1 factor is going to play a very important role in quantum mechanics and even later in quantum field theory. Okay, but it turns out, yes, 2-1 factor plays an important role in quantum mechanics. So one of the von Neumann's favorite result is that if you have a symmetric operator affiliated, I will just say the word, I will not affiliate it with a 2-1 factor.
What do you mean by 2-1 factor? That's something you...
Yeah, the 2-1 factor is what I defined here. So yeah, 2-1 factor is a factor with a trace. Okay, yeah.
Oh, it's a factor with
here,
trace.
huh? Yeah,
but,
so it's a factor with a trace. It's infinite dimensional.
It's a type 2. It's a type 2 von Neumann algebra.
Yes, and this one simply refers to the fact it has a trace.
Oh, I see.
Yeah, so I want to state the result due to von Neumann. So sort of in support of his thought that the 2-1 factor might play a very important role in quantum mechanics. So if A is symmetric affiliated with a type 2-1 factor, then A is self-adjoint. So the A has self-adjoint closure. So let's say that's just right, self-adjoint. Okay. So back in the days, you know, in quantum mechanics, proving that the Schrödinger operator is self-adjoint takes major effort, right? So back in those days, those are what people are interested in. So when von Neumann proved a result like this, he thought that 2-1 factor is going to play a major role in quantum mechanics. And also because of this continuous geometry, they think he might even play an important role in quantum field theory. But sort of the development history sort of not what he predicted. So what happens is, of course, from, you know, this is what I didn't describe before. So we have 3 types of factors. So what happens is that in quantum field theory, type 3 factors appear everywhere. So, and the general conditions, all the observable algebras coming from quantum field theory, all type 3 factors. So, but the lessons we learned from type 2-1 will also play a very important role. I don't have time to discuss it today, but I guess I will start next time by discussing index theory for 2-1 factors and then move on to type 3 case. Okay,
so here,
I think that's...
your type 2 is with a trace.
Yes.
Is that right? But
yes.
1 also means a trace. So
okay, yes,
I'm
yes.
confused.
Okay, so yeah, let me clarify this. So there's a type 2. So type 2 means that either type 2-1 or type 2 infinity. So what is type 2 infinity? Type 2 infinity is just type 2-1 tensor product with B of H, where this H has infinite dimension.
Okay.
Yeah. So yeah. So mostly we just focus on type 2-1. So this has a trace, but this one doesn't have trace. But you know, a major piece of this has a trace. Okay. And the infinite dimensional piece is sort of under control in some sense.
Okay.
Yeah. All right. Okay. I think that's all I want to say today. Thank you.
Well, thank you very much. Oh, it's really helpful. And there's things about the subfactor. And are you ready to give some definition of subfactor?
Yes, yes, absolutely. I can give you the definition right now. I can give you the definition. So I have LF2 already a factor, right? What is a subfactor? A subfactor is just a subalgebra of this von Neumann algebra, which is also a factor.
I see.
Yeah. In fact, that's I will define the index next time, and then we move on to type 3 case.
Okay. So if that's the index of this subfactor would relate to some this what do you call this
quantum dimension.
Quantum dimension, yeah. Yes. That's just amazing.
Well, I think Xiao-Gang, this is the point of the people of this guy. So it's only in the infinite dimensional case you can do this self-referential, which is you can embed yourself into yourself in a proper way.
That's true.
Okay.
Yeah, that's true.
That's what happens to this subject. I have a question, Feng, for you. So it's known there's an algorithm. So you said that you have 2-1 factor, the trace is any real number, right? So it is an algorithm to construct. If you give me a number, a real number between 0 and 1, it is an algorithm to construct a projector to realize that trace?
to realize, yes, absolutely. So yeah, Zhenghan, so let me give you a mental picture of this.
No, I want an algorithm.
I'm sorry?
I want an algorithm. It's a computer science question.
Yes, yeah, I understand that. Yes. So yeah, at least in one case, I guess LF2 is not terribly convenient one. So if I change the group G to permutation group infinite many letters, okay, then it's easy to see how you can construct the projections of whose trace can be any number between 0 and 1. Okay. So think about the 2x2 matrices.
Okay.
And think about the tensor product of these 2x2 matrices.
Okay.
You see 2x2 matrix. If I normalize it, I can get any projection whose value, of course, is a rational number. But only rational number can be approximated, right?
Yeah. Okay. I think I see your point. You can do binary expansion of the real number.
Yes. Exactly. And then I just find enough. And the nice thing about the infinite dimension, this is the reason you have the continuous geometry, because it's large enough, so any of these matrices can be embedded into it.
I see. But I think my question must still be open, because we don't know how many, right? We don't even know the group polynomial algebra L, F2, F3 are different. So
yes, that's a famous question. Yes.
So probably it's very difficult if I give you an arbitrary ICC group. I'll ask you to construct a projector for any real number. Do you think it's known, or you think that's unknown?
I have never thought about that question.
Well, I have two. First I want an algorithm. Second, I want the complexity. In terms of the number of generators.
I see. Okay, I see. Well, that's actually quite simple, because yeah. Now I remember. So even in the free group case, right? So what you do is you just, instead of taking 2 generators, just take 1 generator.
Okay.
That 1 generator would generate a abelian phenomenon algebra, right?
Yeah.
And we know all the abelian phenomenon algebra would be L infinity of some on some space.
Yeah.
Okay. So let's say it's L infinity 0 and 1.
Okay.
And then projection would be simple, right? You just take a characteristic function, with support on from 0 to p to whatever the irrational number you have between 0 and 1.
Okay.
That characteristic function is going to be a projection,
okay.
And its trace is going to be the desired value.
Okay, but that does not solve the question. That just reduce the problem to, is the proof every abelian phenomenon algebra is L infinity into a constructive proof?
Yes, that's true. Yeah.
I don't know, the proof might be constructive. Then that's the answer to the question. So basically, in the group phenomenon algebra case, just take 1 unitary element. That will be enough. So I think once again, I'm not I don't know this complexity theory and so forth very well. So yeah. But anyway,
I'm afraid that's all I can offer.
Okay.
There are other questions for Feng?
Yeah, I don't have a question, but I wonder whether you can save the notes and maybe email us.
Yes, absolutely.
Yeah,
yes, I can.
You're right. So that we can refer back.
Yeah. Sure. Yeah, maybe I will send it to Zhenghan.
Yeah. Please do. Yeah, because I have to admit, I listened to this maybe to you 30 years ago. I didn't get much out of it, but this time I did.
Yeah, but it really helped, because I heard a lot of these words and I have no idea what that means. But now those words really have explained. Yeah.
Okay, that's good to know.
Yeah. And I still thinking about this limit. Right now, I'm thinking about maybe as a remark, is as you know, the infinite Hilbert space is approximated from finite dimensional Hilbert space. Okay, but however, I think in physics, this infinite dimensional Hilbert space also have a structure, which is have a tensor product decomposition in many cases.
Yeah.
So therefore, we'll consider infinite dimensional. We'll consider tensor product decomposition for many small Hilbert space, which is a very high dimensional Hilbert space. Then the subspace can be tricky because whether how subspace fit within the tensor product decomposition you have all kind of choice. You know what I'm trying to say is that maybe this how you embed this how you choose this subspace is a way correspond to way to choose different topology. What I really try to say is that you're just thinking about infinite dimensional vector space as an approximation, as a limit of a finite dimensional vector space may not be a whole story. And so there's a locality somehow. And then when you have if the infinite dimensional vector space is a tensor product of many finite dimensional vector space, and then you choose some subspace of this infinite dimensional vector space, then there's all different choice.
Yes.
And so this pair, the infinite dimensional vector space plus its a subspace, then you take a dimension go to infinity, and then you study the subspace. Maybe that's I don't know whether that is a situation to have to define different topology. What I try to say is that I'm trying to imagine a situation where by taking the limit, you can review or see this different topology or different way to do this algebra. Because I kind of firmly believe that everything can be understood by taking limit. But however, if you don't have a tensor product structure, maybe one don't see such rich things. But once you have a tensor product structure, maybe then the structure we see probably is correspond to this Van Neumann algebra or some other algebra. Yeah, that's my feeling. Yeah.
Yeah. I guess you know, one of the approaches, you know, I've seen people doing statistical mechanics is that they do it on the lattice first.
Yes.
And then take the lattice size and go to 0 and take the limit, right? And that's always a tricky issue. Yeah. So, you know, my view on this is that that's very helpful because it helps us to get the intuition. But there's also an advantage, but just doing it on the continuum limit, you know, on the continuum. So I guess that's sort of the point of view of, you know, just going to infinite dimensional space directly, and yeah. So.
Yeah, I totally agree with you. Doing that at infinite dimension directly helps. But what I'm trying to guess is that what does that mean from physics point of view? You know.
Yes, absolutely. Yes,
you know,
yes, I understand.
Since you can, when you have unidimensional Hilbert space, there's a many different way to do topology. And what that mean is what is the meaning of the different choice of topology? Okay, the reason I'm really getting at is really following. You know, when you have a tensor product structure, you have a dimension. Say like you can have a small Hilbert space lined up in a line. So you have one dimensional, we call one dimensional system.
Yeah.
Or you can have a two-dimensional system where this finite dimensional vector space form a two-dimensional graph.
Yeah.
And their tensor product give you infinite dimension. So therefore, infinite dimensional vector space have many different meaning in it. I mean, some kind of, whether it's coming from one-dimensional system or two-dimensional system.
Yeah.
And so I hope somehow this topology one choose can see this whether what underlying is a one-dimensional or two-dimensional system in physics. And that may correspond to the, I wonder that. So actually that's really raise a question. Maybe this Van Neumann algebra or this weak topology, whether that's correspond to one-dimensional system. because the result one may get is looks like some kind of conformal field theory results. That's like a one dimension. Then one may say, suppose you have a two-dimensional system. Maybe that corresponds to infinite dimensional Hilbert space with some different choice for topology. We'll do two-dimensional system. I wonder whether there's something along this direction.
Well, I think it really depends on the Hamiltonian you use, right? What kind of interaction you put in there. So yeah. As a Hilbert space, they're, I mean, abstractly isomorphic, but I think I guess after that you want to get your algebras, observable algebras, and that depends on the dynamics, or exactly. you put on the system. So yeah. So
this observable so-called local, this algebra of local operators carry information of a dimensionality of a space. Like a one dimension, two dimension will be different.
Yes, of course.
So then there's an issue that how this dimensionality of a space is captured in this setup. That's a.
Let's see.
So I don't know whether my impression is right or not. Looks like the setup you described today maybe capture the operator algebra of one dimension. Or maybe I may be wrong. I just throw out some question. One dimension, two dimension algebra, at least from physics point of view, is very different. And whether the present setup is really suitable for one dimension only. So maybe that's a question. Yeah, that maybe one can see whether that is.
Well, I guess I didn't quite see it. So I didn't really discuss any system yet. So it's basically concepts, the notion, the definition. I think the notion I introduced today apply to any dimension, any system. Yes. So all these things will show up in systems, but of course the observable algebra will be different. The dynamics will be different. Yeah.
I see.
So
maybe that's additional structure. Okay. I see. Yeah, I agree.
I have a question here.
Yeah.
You have said that the L of F2, right?
Yes.
Actually, is very different from the B of H.
Yes.
I can see an important feature of L of F2, namely, there is a group action acting on it, right?
Yes.
So then my question is, where are the crucial features that makes, not features, I mean concept or definition, which requires the G action, the group action?
So LF2 is an example, which, the reason I chose this example is because it's convenient, and especially for people with a representation background, it sort of come naturally because this is the left regular representation. But of course, and I take advantage of that, right? So I have, I have the trace can be well defined, it's easy to define. But of course, in general, 2-1 factor, that is for Neumann algebra with a trace, they may not come from groups. I mean, there are various ways, there are other ways of constructing 2-1 factors. What I presented is just a convenient way. So it's a convenient choice. So in general, the type 2-1 factors might not be associated with any group action. Okay, it can be very abstract. It's just for Neumann algebra with a trace. Okay, so, yeah, so the example presented has representation theory flavor, and it's convenient.
So my question is, however, if you have a group action, then you must get a type 2-1, or actually it could be also something else.
Yes. So the group action I'm taking is a very special one. It's the left regular representation. This is one, one very special, and it's special in the sense that you always get 2-1 factor in this way, because that tracial property is always true for any discrete group. Okay, so it's a very special group action. If you take other group action, you will get all kinds of crazy factors out of this. Yeah, so there's a flood of examples coming out of this. So for instance, you can produce uncountably many non-isomorphic 2-1 factors. So it's a huge zoo out there. Yeah.
Yeah. But actually, Feng, I have a question here. So among this, uncountable many, what's this easiest example which is not a group subfactor, not a group factor?
Sorry, Zhanghai, I may have misled you. So the uncountably many examples constructed all come from groups.
Okay.
That's the first construction.
Okay.
But of course, the other examples. So let me see if I can have an easy example of non-group 2-1 factor. It's actually, that reminds me. So the first example was constructed by Alan Kong back in the 70s. So it's not easy. In other words, it's not easy. Yeah.
It's a paper.
So let me just tell you. So see, he used property T to get an example of a non-algebra which is not isomorphic to its opposite. So that all the group for non-algebra has the property that is isomorphic to its opposite.
Okay.
So that's Kong's construction. So it's not easy example.
I see. So it's pretty subtle.
Yeah. I have a question about this BH. You say BH have no trace.
Yes.
My question following is that, but you can try to define a trace. I mean, to add some structure. Then after adding this structure, then the BH will have a trace. So I'm a little confused. On one hand, this LF2 have a group action.
Yeah.
And the BH don't have a group action, so they are not the same. So in a sense, you say BH have no trace just because you didn't define the trace, but you can try to define a trace in it, then these two will be equivalent. I'm confused.
Yeah,
I'm confused about this point.
Yeah. So maybe I'll go back to my previous. I guess it's. Let's just say it. So if you B of H has a trace, so this trace restricted any finite dimensional subspace would be like it would be 1 over the dimension of n and sum over the diagonal, right? But then you see, there's no way you can make that to be well defined to be along all the ends. You see what I'm saying?
Okay.
Yeah. So that's the difference between the infinite dimensional case and finite dimensional case. Actually, like I said, it's a fun exercise to check that to just show just from the definition there's no if there so in other words you argue if there's a trace and then you reach a contradiction at 0 equal to 1.
Oh, I see. Yeah. Basically means that you cannot define a trace on B of H.
Yes, when H is infinite dimensional. Yes.
Okay.
You can only define it when H is finite dimensional.
But LF2 also infinite dimensional, but somehow there you have a trace.
yes, that's the beauty of it. So in fact, so you see, LF2 is contained in the B of H, right? So that functional is also well defined in B of H. But it's only on restricted that subalgebra, it has this tracial property.
Okay.
Yeah.
I see.
Yeah. So it's actually one line, maybe 2 lines of computation. Just when you do the computation, you realize you have to use the fact that the operator you use of that special form.
Okay.
As soon as you're outside that LF2, then things all hell break loose. So.
Okay.
Yeah.